Hello, everyone. My name is Patrick, and we are the Solar District Cup team from the University of Colorado Boulder. So our problem statement as given to us was design a solar, photovoltaic, and battery storage system that is financially viable and provides the highest energy offset for New Mexico State University to aid in their sustainability goals. Next slide. Like I said, my name is Patrick Gibbs. My primary focus on this project was open DSS modeling.
I'm Allison Kesnick. My primary focus was solar modeling.
Our other team member was Otto Lucas. His role was financial modeling and regulation. My name is Joseph Wilson. My primary focus was OpenDSS modeling.
I'm Alex Rubino. My primary focus was solar modeling.
My name is Michael Michelini. My main focus was financial modeling and regulation.
Over the course of designing our final system, there were goals and guidelines that pertain to NMSU and the Solar District Cup that we had to keep in mind. NMSU is aiming to reach carbon neutrality by 2050. Additionally, as part of their master plan, they are promoting placemaking and sustainability initiatives on campus. The Solar District Cup requires the inclusion of PV and battery storage in the final solution for the project. It also mandates that the system target an NPV of 0 and does not allow for net metering.
For our design approach, we developed photovoltaic rooftop installations, parking covers, and aesthetic installations throughout the campus corridor and student quad. We also installed enough storage to achieve 50% of the critical load during a power outage. We assessed the impact of the PV and battery systems on the grid and ensured these designs are both efficient and cost-effective. Next slide, please. Our PV systems were modeled using Aurora Solar. We generated models for every building with a demand profile for a total of 10 rooftop buildings designs. We also modeled parking lot installations for every lot in the corridor and shaded aesthetic installations for the student quad. Finally, we experimented with ground mount installations in the off-campus open space, but did not include any in our final designs. In order to ensure our rooftop designs were operating as efficiently as possible, we ran an iterative parametric analysis of 2 key design parameters: panel azimuth angle and panel row spacing. We compared 4 outputs: the performance ratio, percent of shading losses, total annual production in kilowatt hours, and numbers of panels and inverters. We selected a final panel azimuth of 170 degrees and a panel spacing of 30 inches because it produced the largest amount of energy out of our set of variables, and it had relatively low shading losses and an acceptable number of mechanical components.
The final system was sized to allow for maximum energy offset without ever providing more energy than could be consumed or stored in the battery at any given time in order to minimize curtailing and energy waste, since net metering was not allowed. The final installation sizes can be seen here along with index labels. The parking lot installations and the rooftop installation on the Corbett Center were the largest, while the quad installation was by far the smallest, and the total installed capacity was 3,780 kilowatts. Next slide, please. To visualize the previous slide, the final design locations can be seen on this map. All rooftop installations are shown in blue, parking lots in green, and the quad installation in orange. The final installations were all in the quad and corridor areas. The open space, which was mentioned in the design approach, was not used in the final installation. Next slide, please.
Just like the previous slide, this is a map of campus that shows the transmission lines on campus from the buildings and photovoltaic arrays to different points on campus. Next slide, please. During this final design process, we developed a 1-line diagram to show how the solar arrays are connected to buildings and to the rest of the grid in Las Cruces. You can see the transformers that regulate voltage across the grid are connected to each building and to each solar array. New solar arrays, we installed transformers to help regulate voltage across the grid. Next slide, please. We took our final system design and modeled it in OpenDSS. Our analyze in OpenDSS showed us that we needed to add new transformers at new array locations. Our initial results showed that the new solar arrays increased the voltage drop across the system. We determined that we need to upgrade transmission lines with lines that have a lower resistance to reduce voltage drops across the grid. With these upgrades, the system voltage stays within the regulated bounds. Next slide, please.
To determine the optimum size of our battery installation, the team used re-uplight. There are several key inputs needed for this program, including electric schedule, panel tilt, azimuth angle, as well as other parameters which will affect the output. The economic objective output by re-uplight was not considered by the team because it did not align with the other economic analyses we performed. Instead, the resilience objective with a 50% critical load was chosen. This means the battery system was designed can supply 50% of the school's critical load when needed, even during an outage. Specifically, it was modeled for a 2-hour outage on the day and time of peak demand and the load profile we were given. The output of the resilience objective yielded a battery system size of 7,399 kilowatt hours and 2,924 kilowatts. Next slide, please. The final battery system design offers 2 main benefits for NMSU. In addition to the improved energy resilience detailed in the previous slide, the battery system improves economic viability through peak shaving. Peak shaving is an implementation strategy where energy stored in the battery is discharged specifically during peak times of peak demand for the university. This helps to reduce peak demand charges, and the implementation of this strategy results in a savings of over $83,000 in year 1, as well as avoided outage costs of over $33,000 after year 1. Converting these savings values into the cash flows, the result is an effective PPA rate of $0.168 per kilowatt hour. Next slide, please. So the system design is fully compliant with all relevant regulations, ranging from international building and fire safety codes to local zoning ordinances. The zoning restrictions for the system are laid out within the City of Las Cruces Land Development Code. Construction regulations are detailed in Chapter 14 of the New Mexico Administrative Code. Additionally, the system design aligns perfectly with the goals of the NMSU Master Plan 2017 to 2027. Relevant permits must be acquired from city, county, and state governments before construction can begin. Next slide, please. The Gantt chart for the full construction process can be seen here. The first steps include performing a structural analysis of the rooftop locations, as well as beginning the permitting application process. These steps can begin immediately. The permitting process will include the acquisition of construction permit from the Doña Ana County Building Services Department, a special use permit from the Las Cruces City Council Planning and Zoning Commission, an electrical wiring permit from the New Mexico Construction Industries Division. Over 6 months scheduled for full permitting process as recommended by the U.S. Department of Energy and the Solar Energy Industries Association. On-site construction is scheduled to begin directly after the spring 2021 semester. Disruptive construction process, such as the parking lot and the open space enclosure, to be complete during the summer of 2021. Full implementation and operation is scheduled to be done by October 2021. Next slide, please.
So here are some of the sources we use to estimate the capital costs of the system. This chart is for the PV capital costs in dollars per watt. We used a linear regression to determine the dollars per watt value for our project, since it didn't exactly fall on one of the sizes listed in this graph. Additional costs were added as necessary to this price. For example, our system includes both carports and microgrid upgrades. Therefore, additional capital costs were added to the structural and electrical balance of system portions of the project. Next slide, please. So here are the estimates for both the energy and power costs of the battery. We estimated the price for the year 2020 and went with the mid estimate to be conservative. Next slide, please. So here's a summary of the key economic outputs from our financial spreadsheet. The PV capital cost is based on the nameplate capacity of system and not the production. As was seen in the previous slides, this dollar per watt value can be broken into different components, such as the engineering and design, as well as modules and inverters. Battery energy costs represent the cost of the energy components of the battery, such as the battery pack, and battery power costs represent the cost of the power components of the battery, such as the inverters and balance of system. And splitting them allows for optimum economic maximization of the battery. All other values in the table here were assumed from NREL studies or were requirements for the project. The discount rate can be especially difficult to estimate, therefore we assumed the values stated for typical utility scale PV projects. Next slide, please. Here's a summary of the key economic outputs from our financial spreadsheet. The PPA rate was calculated based off the MPV of 0, which was also stated as a project rule. The PPA rate is a flat rate per year that NMSU would pay for the electricity produced by the solar PV system, and capital costs for the solar and battery were based on the values presented in the last tables. And as can be seen, this project will be quite expensive due to its size and the fact that batteries are somewhat uneconomical at the moment. And the O&M for year 1 is presented here. However, this value escalates at 2% per year and is even higher in year 10 due to inverter replacement. Next slide, please. So here are some of the key results for the project. The system production is stated for year 1. However, it's expected that the panels will degrade by 0.5% per year. So the production value will decrease every year. Costs, including interest and O&M, nearly exceed $20 million, which was expected and resulted in a very high PPA rate compared to the original price of electricity for the school. However, the system still provides the school with resilience during outages and energy offset for the school. Next slide, please.
Bringing our final design back around, here's how it lined up with the goals of the competition and the campus. For NMSU, this system design provides an approximate carbon offset of 2,270 tons annually, which is a substantial step towards carbon neutrality.
In order to promote placemaking on campus, back one slide, please. We added a shaded quad area and shaded parking structures that would both produce solar energy. In order to promote sustainability, the solar installations, such as the quad and shaded area, would be able to be used by the public. Next slide, please.
The final design provides a 16.5% energy offset to the demand profiles provided for the competition, essentially the maximum possible without selling back to the grid or curtailing the installation.
Although the PPA rate is less economic than the current industrial rate, you still have the added value of the resilience with the battery system during an outage. In addition, the PPA rate is not much higher than the current residential electricity rate in New Mexico.
With the increased resilience of the battery storage, we take care of 50% of our critical load and a 2-hour outage on the day of peak demand. This helps mitigate the impacts of outages on campus.
And finally, we sized the system properly to avoid overgeneration and net metering and curtailment as well, which limited our total energy offset.
These are a list of the references we used directly throughout this presentation. Thank you all for coming, and we'll be happy to take your questions.